Welcome to another episode of Chemistry with Bandit and Sunzi. In today's episode, we will explore the scientists' experiments and atomic models that have led us to the modern theory of the atom. Let me warn you ahead of time. There's a lot of information in this presentation to try to help you understand it. However, not very much of it is testable, so be sure to look at your student expectations so you know what is and what isn't testable. Democritus was a Greek philosopher, and he was the first person on record to have the idea that matter was made up of particles that couldn't be split apart any further and still be the same substance. He called these particles atoms, and the name stuck ever since. Aristotle, another philosopher, believed matter was continuous and composed of the four elements earth, air, fire, and water. The idea of the atom did not resurface until the 1600s and 1700s. In the 1800s, John Dalton reestablished the idea of the atom with his atomic theory, known as Dalton's atomic theory or Dalton's postulates. He based his atomic theory on the law of conservation of mass, which says that mass is neither created nor destroyed, which implies that atoms are neither created nor destroyed as well, the law of definite proportions, and the law of multiple proportions. His atomic theory stated that each element consisted of tiny, invisible particles called atoms. The second postulate states that atoms of the same element are identical. This is not exactly true. As it turns out, most elements are made up of atoms with slightly different masses called isotopes. Dalton's third postulate states that atoms cannot be subdivided, created, nor destroyed. This is also not true. While atoms cannot be broken apart, created, nor destroyed in a chemical reaction, they can in a nuclear reaction. Atoms are made up of even smaller particles called subatomic particles. The fourth postulate, atoms of different elements combine in simple whole number ratios to form compounds. And the final postulate, which states that in chemical reactions atoms are combined, separated, or rearranged. Both the fourth and fifth postulates are still true today. Dalton's theory led to the billiard ball model of the atom, neither of which could explain how atoms form compounds and what was inside the atom. Many scientists couldn't see how these tiny invisible particles could cause the things that they were observing in nature and their chemical reactions. However, atoms became widely accepted after 1905 when Einstein used atoms to explain how Brownian motion works. See how the non-living pollen grains suspended in the water move around. This motion is known as Brownian motion, and it is caused by the water molecules colliding with the grains of pollen. The explanation of Brownian motion was definitive proof of the existence of tiny invisible particles such as molecules and atoms. The modern atomic theory is Dalton's atomic theory that has been revised to remove the incorrect parts. Even though the billiard ball model of the atom wasn't correct, it gave scientists a good starting point for investigating the atom. In the 1890s, J.J. Thomson was experimenting with cathode ray tubes and ended up discovering one of the subatomic particles. He discovered the electron. A cathode ray tube is a glass tube with most of the air removed, and it was found that if you place two metal electrodes in the tube and attach them to a high voltage source, the tubes would produce a beam that glowed. They named the beam cathode rays because it came from the metal electrode attached to the negative or cathode side of the high voltage source. These cathode rays are what we now call electrons, and are produced the same way an electrical spark is. But with most of the air removed from the tube, it produces a continuous stream of electrons. By placing a hole in the anode, they were able to produce a focused beam of electrons that they could experiment with. Additionally, they coated the end of the tube with a phosphor. A phosphor is a compound that will glow when struck by fast-moving particles, such as electrons or neutrons. This gave them a way to see where the beam was and how the beam was affected by different variables such as an electric or magnetic field. Thomson was able to determine that electrons were negative because like charges repel, and the beam of electrons was deflected away from the negatively charged plate. Thomson was also able to prove that the electrons was a particle that has mass, because when the beam of electrons was fired at a paddle wheel, the wheel spun. As you can see in this video, the beam of electrons causes the paddle wheel to spin. There are different types of cathode ray tubes. Thomson also found that no matter what metal the cathode was made out of, it produced electrons. This told him that the electron was probably a fundamental particle that is found in all matter.
Mr. Harbinger, cats are so stupid. Miss Kitty wanted to fly to Oklahoma, and she told the airline that she didn't want a window seat because the wind would mess up her hair.
With the discovery of the electron, it disproved Dalton's billiard ball model, so Thomson proposed a new model called the plum pudding model. In the plum pudding model, the atom is a positively charged sphere with electrons embedded in it like raisins in a plum pudding. In 1910, Ernest Rutherford decided to test the plum pudding model by firing radioactive alpha particles at a very thin sheet of gold metal. Rutherford expected the alpha particles to pass straight through the gold with little or no deflection. What happened blew their minds. Most of the alpha particles did go through with no deflection, some were deflected at small angle, and a few bounced almost straight back. They compared it to firing a cannon at a piece of tissue paper and having it bounce back and hit you. To learn more about the gold foil experiment, you can watch these videos by clicking on the link in the presentation file. The results of the gold foil experiment are as follows. The atom contains a very small volume of space with a lot of mass that is positively charged. We call that volume of space the nucleus. When most of the alpha particles pass straight through the gold foil, it showed that the atom is mostly empty space. The alpha particles that were deflected by small angles were caused by the positively charged alpha particles passing close by the nucleus of the atom, proving that the nucleus is positively charged. The alpha particles that bounced back were caused when the alpha particles struck the nucleus. Rutherford was able to determine that the nucleus was very small due to the few number of alpha particles that deflected at a large angle. He was also able to determine that the nucleus contained a lot of mass because the alpha particles bounced almost straight back from the foil. The gold foil experiment disproved the plum pudding model and resulted in the nuclear model of the atom. Rutherford's experiment showed that most of the mass and all the positive charge was in the nucleus. It also showed that most of the atom was empty space and the electrons were dispersed around the nucleus. At the time, it was known that in a neutral atom, the number of protons is equal to the number of electrons, and that electrons have a very small mass. The number of protons and electrons in the atom did not account for all the mass of the atom. It wasn't until 1932 that James Chadwick was able to identify a neutral particle, the neutron, that is also located in the nucleus. Rutherford's planetary model of the atom is also called the nuclear model. In this model, the electrons orbit the nucleus like planets orbit the sun. However, it was soon realized that this model had a major flaw. Bodies of mass orbiting a larger body in space are constantly slowing down and losing energy so that eventually they fall out of orbit and crash into the larger body. The same thing would have happened to electrons. They would eventually slow down and crash into the nucleus. Scientists could find no evidence of this happening. It was soon realized that classical Newtonian physics could not be used to describe an atom.
Papa.
Yes, Senzi?
Did you hear about the Italian chef who died?
No, what happened?
He passed away.
This brings us to Niels Bohr. In an effort to explain how electrons changing energy levels within the atom produce photons of light, he comes up with Bohr's model of the hydrogen atom. It's the model of the hydrogen atom because it only works perfectly with single electron atoms like hydrogen. To understand Bohr's model, we need to know a little bit about gas discharge tubes and line spectra. It was found that if you build a cathode ray tube where all the air is removed and replaced with a small amount of an element, it produced different colored light. These are now commonly known as neon lights. It was then discovered that if you take the light from a gas discharge tube and pass it through a prism, it doesn't produce all the colors of a rainbow, but instead it produces lines of different colored light at different wavelengths. A spectrometer is an instrument used to separate light and visualize the spectrum. For example, sunlight would produce all the colors of the rainbow, while a gas discharge tube would produce a line spectrum. Sunlight and starlight produce an absorption line spectrum, where all the colors of the rainbow are present, but there are dark lines in the spectrum. The dark lines are missing wavelengths of light. On the other hand, gas discharge tubes produce an emission line spectrum, where most of the spectrum is black with bright lines of light. A line spectrum can be used to identify an element, just like a fingerprint can be used to identify a person. Each element has a unique line spectrum that can be used to identify which elements are in a sample, in the sun or other stars, and in the atmosphere around faraway planets. Here are some examples of emission line spectra. It is important to note that with an emission line spectrum, there may be lines of light that we can't see with our eyes, such as ones that fall within the infrared or ultraviolet light range. In 1913, Niels Bohr developed a model of the hydrogen atom that explained how the line spectrum of hydrogen is produced. He found that electrons exist in energy states that can only have certain amounts of energy. It can be thought of as if climbing a ladder. You can stand on the first rung, or the second rung, or the third, or the fourth, and so on, but you can't stand in between the rungs. It's the same with energy levels of an atom. An electron can have an energy that puts it in the first energy level, or an energy that puts it in the second energy level, or the third, or the fourth, and so on, but they can't have an energy that puts it in between energy levels. An electron in the lowest energy level that it can occupy is said to be in the ground state, while an electron that is in a higher energy state, when there are open energy levels below it, is said to be in an excited state. Bohr found that hydrogen's one electron would normally be found in the first energy level or its ground state. He also found that the electron could absorb photons of light, but only certain photons of light with the right amount of energy. Hydrogen's electron could absorb a photon that had the right amount of energy that would put it in the second energy level, or the right amount of energy that would put it in the third energy level, or the fourth, or the fifth, and so on. Bohr also found that an excited electron will eventually fall back down to its ground state, and when it does, it gives off a photon of light that has the same amount of energy as the energy difference between the energy levels in the hydrogen atom. Photons of light that have different energies have different wavelengths and therefore are a different color of light. Bohr was able to come up with a mathematical equation to calculate the energies of the different energy levels of the hydrogen atom, which corresponds exactly with the different colors of light found in the line spectrum of hydrogen. For example, he determined that the blue-green line in the line spectrum is produced when an electron moves from the fourth energy level down to the second energy level and gives off a blue-green photon of light. Even though Bohr's model only works perfectly for the hydrogen atom, it still explains how all light in the universe is produced. While Bohr's model doesn't actually show the correct structure of the atom, it is still the best way to draw an atom to show all the subatomic particles. De Broglie determined that while electrons are particles, they also behave like a fixed standing wave, which, just like electrons in an atom, can only have certain energy levels. Because electrons are particles that also behave like a wave, they are said to have a dual wave-particle nature. So instead of an electron having an orbit, or physical place in time and space around the nucleus, it follows a wave pattern. So the properties of the atoms as we know it today. The atom is electrically neutral because it has the same number of electrons as protons. The nucleus is spherical in nature, positive, contains 99.7% of the mass of the atom. It's 1/100,000th the diameter of the atom, and it is surrounded by one or more negative electrons. The nucleus contains positive protons and neutral neutrons. Use this link in the video presentation file to watch this video on quantum mechanics. To explain the atom, scientists had to invent a new branch of physics called quantum mechanics. De Broglie, Heisenberg, and Schrödinger are some of the scientists that developed the quantum model of the atom. In this model, there are different types of energy levels, but each electron follows the wave function or wave pattern of an energy level called an orbital. An orbital is mathematically calculated using the Schrödinger equation, and it is a three-dimensional space around the nucleus where there is a 90% probability of containing an electron with a specific amount of energy. Just like in Bohr's model, orbitals can only exist at certain amounts of energy, because even though electrons are particles, they behave like a standing wave. They have a dual wave-particle nature. Electrons appear to move randomly within their orbitals. There are different types of orbitals, and they have different shapes. The S-type is a spherical shape, and there is only one kind of S-type energy level. The P-type orbitals are dumbbell or propeller shaped that contain two lobes aligned opposite of each other. There are three kinds of P-type orbitals. There are 5 D-type orbitals. Most contain 4 lobes, while one is a pair of lobes aligned with a donut-shaped region between them. And finally, here are the 7 F-type orbitals. In the quantum model of the atom, the orbitals overlap each other. Shown is the quantum model of a neon atom, with its 10 electrons. As the atom gets bigger, it will have more electrons and more occupied energy orbitals that would make it very difficult to draw and still be able to tell which orbital an electron is in. This is the main reason we still use the Bohr model to draw models of the atom.
Thanks for joining us for another episode of Chemistry with Bandit and Sunzi. Hope to see you again next time.